You know how large language models have truly changed the game, generating text that feels, well, human. But what if I told you they're now evolving beyond just talking to actually doing things autonomously? And not just one AI, but many, working together like a digital dream team. That's precisely what we're diving into today. The fascinating world of LLM-powered multi-agent systems, or LLM-MAS. We've gathered an excellent collection of sources for this deep dive, exploring the very blueprints of how these systems are built, how they collaborate, and what this all means for everything from scientific discovery to the future of how we work. Our goal today is to bring you the essential insights, help you grasp this pivotal moment in AI. So to kick us off, what exactly does it mean for an LLM to transform into an agent?
Well, it's a really profound architectural shift we're seeing. Instead of a single AI working in isolation, we're now seeing entire systems where multiple AIs are designed to collaborate. And this often leads to a level of collective intelligence far beyond what any single model could achieve alone. It really is a new paradigm.
Okay, let's unpack this. We've all interacted with LLMs, right? Maybe asking them to write a poem or summarize an article. They're incredible text processors. But our sources describe a significant evolution for these models, a profound architectural transition, they call it. So what actually transforms a passive text generator into an active, goal-oriented system that can take action?
That's a great question. Because autonomy isn't something an LLM has right out of the box, not inherently. Instead, it's enabled by a surrounding cognitive architecture. You can think of the LLM as the brain, or maybe the reasoning engine it understands, processes, and plans.
I'll get a brain.
And a core difference is planning. An agent can take a high-level objective, like research market trends, and write a report, something quite broad. And it can break that down into smaller, manageable subtasks. It can even refine its plan, adapt as it receives new information or feedback.
Adapting on the fly.
Exactly. And agents also gain memory. This is crucial. Not just the short-term memory, like the LLM's immediate context window for the current conversation.
Right.
But also long-term memory, often stored in an external database, typically a vector database.
A vector database, so it can recall things from way back.
Precisely.
Yeah.
It lets the agent learn and adapt over extended periods. It mirrors, in a way, human working and long-term memory. And here's where it gets really exciting. Agents can use tools.
Tools? Like what kind of tools?
They can integrate with external applications, APIs, databases, you name it. This means they can fetch real-time data, maybe perform complex calculations, or even execute actions in other systems. It basically lets them overcome the limitations of just being trained on static data.
Okay, that makes sense. So it's not just about a single one-shot prompt anymore. Our sources highlight something called the Sense, Think, Act loop. What does that look like in practice? Why is it so fundamental?
The loop is, well, it's the agent's fundamental operational cycle. It's how it lives, breathes, so to speak. First is sense, where it observes its environment. That could be a user query, output from a tool, anything external.
Okay, sense.
Then think. This is where it uses its LLM core, its planning capability, and its memory to decide what to do next.
Right, the reasoning part.
Exactly. And finally, act, where it executes an action, maybe calling a tool, generating a response, sending a message. And this cycle just repeats until the goal is met.
Sense, think, act, over and over.
Yes. And this iterative, stateful meaning, it remembers things between cycles and goal-oriented process, is what fundamentally distinguishes an autonomous agent from just, a simple stateless LLM call.
Yeah.
The ability to maintain state and act over time. That's the essential prerequisite for building these multi-agent systems we're talking about.
That's an incredible leap for just a single agent. Planning, memory, tools, the whole loop. But the real game changer you mentioned is when you combine many of them. What kind of problems open up when you have a whole team of these agents working together?
Yeah, that's where multi-agent systems, or MAS, come in. MAS is basically a computerized system made up of multiple intelligent agents. They interact within a shared environment, trying to achieve common goals, or sometimes even conflicting ones. They're really designed to tackle problems that are too large or too complex for any single agent to handle alone.
And traditionally, these MAS had certain characteristics, right?
That's right. Traditionally, MAS operate with three core principles. First, autonomy agents act independently based on their own state and goals. Second, local views. No single agent usually sees the entire picture. They have their own perspective on the environment. And third, decentralization, meaning there's typically no single central controller telling everyone exactly what to do. Control is distributed.
Okay, autonomy, local views, decentralization. Got it. But here's where it gets really interesting, as you said earlier. Our sources talk about the LLM-MAS paradigm shift. It mentions that traditional MAS often relied on rigid protocols for communication, but LLMs changed the game entirely. How so?
This is the defining innovation, really. It's using natural language as the universal communication medium between agents.
Instead of code or special languages.
Exactly. Instead of formal, predefined agent communication languages, ACLs like KQML you might have heard of, which are like strict grammar rules for machines. LLMs allow agents to communicate with, well, human-like richness and nuance. They can understand context intent.
Wow. So they can just talk to each other like people.
Pretty much. And this enables things like emergent collaboration and dynamic specialization. Agents can fluidly take on roles. Maybe one acts like a CEO, another a programmer in a virtual software company simulation. They can negotiate, adapt their roles in real time based on the conversation.
That sounds incredibly flexible.
It is. It's a fundamental shift from just, let's say, syntactic interoperability, can the messages be parsed, to true semantic collaboration, do they understand each other? Agents grasp intent and context now.
But does that flexibility introduce new problems? You mentioned earlier things like hallucination.
Ah, yes, the trade-off, absolutely. This flexibility comes at a cost. LLM MAS are inherently more non-deterministic. They're less predictable than systems using rigid protocols. And this raises challenges like misinterpretation, one agent misunderstanding another, or hallucination, where an agent confidently states something incorrect.
And these errors could spread.
Precisely. Cascading errors are a real concern. One agent's mistake can influence others down the line. It's a challenge we have to engineer for.
Okay, so you have these powerful communicating agents, but also these risks. So once you decide you need multiple agents, how do you even begin to organize them? Our sources dive into a taxonomy of multi-agent architectural patterns.
Yeah.
What are the big categories? What should someone consider when designing one?
That's a crucial question. Choosing the right architecture is key. At the highest level, you've basically got two main families, centralized and decentralized. Centralized architectures, like the orchestrator pattern, or sometimes called a star pattern, have a single agent coordinating everything. Think of a conductor leading an orchestra.
Makes sense. Simple to manage, I guess.
Yeah, strengths are simpler management, clear control flow. But the weaknesses are pretty clear, too. It's a single point of failure. If the orchestrator goes down, the whole system might stop. And it can become a performance bottleneck if it gets overwhelmed.
Right, okay. And the other type, decentralized.
Decentralized architectures. Think of patterns like network or peer-to-peer. Here, there's no central controller. Agents interact more directly with each other.
Like a social network.
Kind of. Strengths are high robustness, no single point of failure, and they tend to be more scalable. But the weaknesses are increased complexity and coordination. Getting everyone on the same page can be tricky, and they can lead to less predictable emergent behaviors because control is so distributed.
It sounds like there's no perfect solution then, a trade-off either way. So what about hybrid approaches? Or maybe more specialized patterns that try to get the best of both worlds?
Exactly. In practice, many systems are hybrid. They combine elements. For instance, hierarchical architectures are common. You organize agents in layers. Higher-level agents might delegate tasks to lower-level ones, like managers supervising teams who supervise workers.
Okay, like an org chart.
Sort of. And you can make these event-driven, maybe using platforms like Apache Kafka, which acts like a super efficient digital post office for data between agents. This adds resilience and scalability. And another really fascinating pattern is the blackboard architecture.
Blackboard, what's that?
Imagine a shared whiteboard. Agents communicate asynchronously, meaning not in real time back and forth, by writing information, problems, or partial solutions onto the shared blackboard and reading information others have posted.
Ah, so they don't talk directly.
Not necessarily. It decouples the agents. One agent doesn't need to know who will use the information it posts. It's great for complex problems needing diverse specialists who can contribute when they have something relevant.
Yeah.
We also see simpler patterns like sequential, like a pipeline where work passes from one agent to the next, and parallel patterns where agents work on different parts of a task simultaneously.
Lots of options.
Definitely. And if we connect this to the bigger picture, it really all boils down to what architects call the C3 trade-off. Control, complexity, and cost.
Control, complexity, cost. Okay.
Yeah, you're constantly trying to find the optimal balance for your specific problem. You might need tight control, or you might prioritize low complexity, or maybe minimizing computational cost is paramount. What we're seeing now is a move towards more flexible orchestration frameworks. These allow you to dynamically compose these patterns, mix and match, rather than being locked into one rigid, static choice from the start.
Right, that flexibility seems key. Building these systems from scratch, even with patterns, sounds like a massive undertaking, though. Thankfully, our sources mention several leading frameworks that act as sort of scaffolding. What are some of the standout ones? How do they differ?
Frameworks are absolutely critical, yeah. They handle a lot of the underlying engineering complexity so developers can focus on the agent logic. LangGraph is one. It offers really fine-grained control. It uses a graph-based approach, representing the flow as nodes and edges. It's great for complex, cyclical workflows where agents might need to loop back, and it supports stateful, durable execution.
Durable meaning it can save us progress.
Exactly. It can save its state and recover from failures, which is vital for long-running tasks.
Yeah. What else?
Then there's AutoGen from Microsoft. It really excels in multi-agent conversational applications. It makes it easier to set up dynamic group chats between agents and also to incorporate human-in-the-loop workflows where a person can step in and guide things.
Conversational focus. Interesting.
Crew AI is another popular one. It's designed to be very intuitive, focusing on role-playing. You define agents with specific roles and goals, and they collaborate as a crew to achieve an objective. It's fantastic for rapidly prototyping structured business processes.
Like setting up a virtual team quickly.
Precisely. And one more that's quite fascinating is ChatDev. This one is highly specialized. It actually simulates an entire virtual software company.
A whole company. Seriously.
Yeah. Agents take on roles like CEO, programmer, tester, designer. They collaborate sequentially following a kind of waterfall process to automate the software development lifecycle right from a natural language prompt. It even uses clever mechanisms like communicative dehallucination, where agents cross-check each other's work to try and reduce errors.
That's incredible. A virtual software house. It sounds like there's a real spectrum here then. From frameworks giving you deep granular control like LangGraph, to others offering higher levels of abstraction like True AI for faster setup. So what does this mean for someone trying to choose the right framework? And where is this heading? Is everyone building their own thing or?
That's a critical question for any developer or architect. Are you prioritizing that fine-grained control maybe for a really complex custom workflow? Or do you need higher level abstraction to get something up and running quickly? It's a key design decision based on the project's specific needs and constraints.
Right. Control versus abstraction.
Exactly. And looking ahead, the field seems to be moving toward a more modular, interoperable landscape. People are realizing that different frameworks have different strengths. There's a proposed standard called the Agent Protocol. The aim is to define a common framework-agnostic API like a universal language or set of rules for inter-agent communication.
So agents built with different tools could talk.
That's the goal. Think of it like creating a universal translator. It would mean you could potentially mix and match the best agent for each specific function, regardless of which framework it was built with. You could have a LangGraph agent doing complex planning talk to a Crew AI agent handling task execution.
That would be powerful. A truly collaborative ecosystem. Okay, so we have the architectures and the frameworks, but beyond the basic structure, our sources delve into advanced design patterns for more robust enterprise-grade systems. What are some of the clever ways these systems share knowledge effectively, or learn together, or even manage their own roles?
Yeah, as systems get more complex, you need more sophisticated mechanisms. Knowledge graphs are becoming increasingly important.
Knowledge graphs, how do they help?
They provide a shared, consistent, structured knowledge base that all agents can access. Think of it as a central library or database of facts and relationships. This helps ground the LLMs, reducing hallucinations because they have a reliable source of truth, and it enables much better coordination because everyone's working from the same information.
A shared brain, almost.
In a way, yes. Then there's multi-agent reinforcement learning, or MRL.
Reinforcement learning, but for teams.
Exactly. MRL allows agents to learn how to interact optimally over time through trial and error. They get rewards for achieving goals, especially goals requiring coordination. It's like applying game theory agents figure out the best strategies by literally trying things out and seeing what works best for the team.
Learning by doing together.
Right. And for situations where data privacy is critical, there's federated learning.
How does that work?
In federated learning, agents train their models on their own local, potentially sensitive data that never leaves their environment. Then, instead of sharing the raw data, they only send encrypted model updates or summaries to a central server, which aggregates them to improve a global model.
So the private data stays private.
Precisely. This is crucial for regulated industries like healthcare or finance, where you need collaboration without exposing sensitive information.
Makes sense. Now, one thing that really stood out to me was dynamic role assignment. Our sources say LLM-based agents can fluidly shift their functions. How does that actually work? What are the implications if an AI's role isn't fixed?
This is one of the most remarkable aspects enabled by LLMs. The shift from formal, predefined role changes maybe updating a config file to what you might call implicit or soft role assignment.
Soft assignment.
Yeah, a supervisor agent or even a human can simply alter an agent's natural language instructions. You could tell an agent, okay, now act as a data researcher and find relevant papers, and then later, right, switch gears, now act as a technical writer and summarize those findings.
Just by telling it.
Just by telling it.
Okay.
Its role, its function seamlessly shifts based on the prompt, the conversational context.
That offers incredible flexibility.
Tremendous flexibility. But it also introduces a critical challenge, particularly for governance and accountability. Well, it becomes much harder to definitively audit an agent's designated responsibility at a specific point in time when its function is constantly being redefined by these transient conversational instructions. Who is responsible for that decision if the agent's role changed 5 minutes before?
Yeah, tracing responsibility gets blurry.
Exactly. The core insight here is that this amazing flexibility forces us to completely rethink how we assign and audit responsibility in these highly dynamic autonomous systems. The ambiguity is a direct consequence of the power of natural language control.
That's a really important point.
Yeah.
So related to that, when these agents, perhaps with different roles or even just different perspectives derived from their local views, need to agree on something, how do they negotiate? How do they reach consensus?
Negotiation is absolutely fundamental, yeah, for resolving conflicts, allocating resources, agreeing on plans. Beyond the simpler mechanisms like auctions or the classic contract net protocol where tasks are bid on, we're seeing more sophisticated approaches emerge, especially with LLMs. One is argumentation-based negotiation.
Arguing like humans.
Almost. Agents don't just state their preference. They provide reasoned arguments for their positions, drawing on their knowledge or goals. It's more like a structured debate to find the best outcome.
That's fascinating.
It is. And this brings up another crucial consideration. Research into what are called LLM deliberation games. These studies benchmark how well LLMs perform in tasks requiring logical reasoning, strategic planning, negotiation, and even theory of mind, understanding another agent's perspective.
Testing their social intelligence, basically.
You could say that. And what's truly surprising, perhaps, is how an agent's personality, which can be modulated through careful prompting, telling it to be cautious or bold or collaborative.
You can give them personality.
In a sense, yes, through the instructions. And research shows this personality significantly impacts the consensus dynamics of the whole group. For instance, experiments have shown that introducing just a few stubborn agents can cause an entire system to converge on their initial value or opinion. They effectively act as emergent leaders just because of how they're prompted.
Wow. So the prompt defines the social dynamics.
Absolutely. If we connect this to the bigger picture, it means concepts we usually associate with psychology or social sciences like personality are now becoming first-class engineering primitives. We're actively designing and shaping the culture of an agent society through prompts and architecture.
This is where it gets really interesting for me and maybe a little mind-bending. Our sources highlight emergent behavior, these complex system-wide patterns that just sort of arise spontaneously from all the local interactions between agents, behaviors that can often surprise even the system's designers. Can you give us some vivid examples of this happening, where the whole is more than or just different from the sum of its parts?
Absolutely. Emergence is one of the defining characteristics of complex systems, including MAS. A classic example is swarm intelligence. Think of simple robots or even simulated amps. Each one follows very basic rules. Avoid collisions, try to stay near others, maybe a line direction. No central controller tells them to flock or forage efficiently.
But they do it anyway.
But they do it anyway. That complex, coordinated group behavior flocking, collective searching emerges spontaneously from those simple local rules. Another really compelling, maybe slightly unnerving example was the 2017 Facebook AI experiment.
Oh, yeah, I remember hearing about that.
Right. Two negotiation chatbots were tasked with bartering over items like books or hats. And what happened was they spontaneously invented their own highly efficient non-human language between themselves to optimize their negotiation outcomes.
They made up their own language.
They did. It wasn't explicitly programmed. It emerged from their core goal of effective communication and negotiation. It was more efficient for them than English, apparently. Or think about multi-agent reinforcement learning simulations. You might set up a game of hide and seek with simple rewards for hiding or seeking. And over time, agents spontaneously develop specialized roles and strategies, like some becoming scouts to find the hiders, others becoming blockers or defenders to protect teammates, all without explicit instruction to do so. The strategies emerge.
That's incredible. It really highlights the potential creativity and adaptability of these systems. But if these behaviors are unpredictable, sometimes even surprising the creators, does that also introduce significant risks? Our sources talk about a duality of emergence.
Yes, absolutely. Emergence is fundamentally a double-edged sword. It's the source of innovation, adaptation, and unexpected solutions, but it's also a source of significant risk and unpredictability. We've already seen real-world examples like flash crashes in financial markets, which are often attributed to the complex, emergent interactions between automated trading
Like
agents.
unintended consequences.
Exactly. And the broader implication here, especially for LLM-based MAS, is that you actually have two layers of emergence potentially compounding each other.
Two layers. How so?
First, you have the emergent abilities within a single powerful LLM, things like advanced reasoning or few-shot learning, which weren't explicitly programmed but emerged from the scale of the model.
Hmm.
And then you layer on top of that the emergent collaborative behavior arising from the interactions between multiple such agents.
Emergent squared, almost.
Kind of. And this compounding effect makes the overall system behavior exceptionally difficult to predict, let alone control or guarantee.
Can you give an example of that risk?
Sure. Consider cascading hallucination. Agent A, maybe a research agent, hallucinates a plausible but incorrect fact. It passes this assertion to Agent B, maybe a report-writing agent. Agent B, trusting Agent A, perhaps based on its role, incorporates this hallucination into its report, which then influences Agent C's decision-making.
And the error propagates.
Right. You get a system-wide failure rooted in an initial hallucination, a failure that might be impossible to detect just by testing each agent in isolation. They might all perform fine individually.
Wow.
Really demonstrates that testing and validating MAS isn't like traditional software engineering where you test components and assume the whole works if the parts do. It's much more like a problem in complex system science. It requires continuous monitoring, dynamic guidance, and maybe even designing for resilience against these emergent failures.
So, given this unpredictability, this double-edged sword of emergence, how do you design systems that not only handle it, but maybe even harness the positive side? How do you actually foster collective intelligence?
That's the million-dollar question, isn't it? Collective intelligence, in this context, is where the group's problem-solving capabilities significantly exceed the sum of its individual members' abilities. It's not just cooperation, it's synergy.
Getting more out than you put in.
Essentially, yes. It relies on distributed decision-making and achieving adaptive, intelligent global behavior from local interactions. Key mechanisms we already touched on help here. Things like effective specialization of roles, efficient information sharing, like with knowledge graphs, and adaptive learning through techniques like MARL.
So using those patterns we discussed earlier.
Exactly. But there are also frameworks being developed specifically to engineer collective intelligence more explicitly. One really interesting example highlighted in the research is the MACI framework, standing for Measuring and Architecting Collective Intelligence.
MACI. Okay, what does it do?
It combines several clever components. It uses something called Socrasynth, which orchestrates structured, Socratic-style debates between agents holding different roles or perspectives. The goal is to surface disagreements and reduce individual agent hallucinations through reasoned argument.
Debate club for AIs.
Kind of. It also uses events to quantitatively measure and guide the dialogue, ensuring it's productive. It includes earlists for internal ethical governance checks within the system, and SIGLM provides a persistent transactional memory system so the collective learning isn't lost.
That sounds incredibly sophisticated.
It is. And ultimately, what frameworks like MECI are trying to do is manage what you might call the epistemic tension in a group.
Epistemic tension.
Yeah, the balance between convergence, the need to eventually reach agreement and make a decision, and divergence, the need to explore diverse ideas, challenge assumptions, and avoid groupthink.
Exploring versus deciding.
Exactly. MCI tries to architect that process, ensuring there's enough creative exploration, but also robust mechanisms for reaching reliable consensus. And connecting back to what we said earlier, the prompt is no longer just an input telling an agent what to do. In these systems, the prompts, the roles, the communication protocols, they become the tools for actively shaping the culture and the collective intelligence patterns of an entire agent society.
Shaping the culture of an AI society. That's quite a thought. Okay, this all sounds incredibly powerful, almost science fiction in some ways. But you've mentioned finance, swarm robotics. Where are we actually seeing LLM-powered multi-agent systems being used effectively in the real world today? What kinds of concrete problems are they tackling?
It's moving faster than you might think and across quite a few domains. Automated software engineering is a big one. We talked about chat devs simulating a virtual company. While maybe not fully replacing human teams yet, tools like this and others are automating significant parts of the development lifecycle: code generation, testing, documentation based on natural language requirements. Agents collaborate as programmers, testers, project managers.
Speeding up software creation.
Definitely. Another huge area is accelerating scientific research. In drug discovery, for example, agents are being used to collaborate across vast biomedical knowledge bases, reading papers, connecting disparate data points, helping researchers formulate and test hypotheses much faster. In material science, systems like atom agents involve specialized agents for running simulations, analyzing data, proposing new experiments for designing alloys or other materials.
So AI research assistants, essentially.
Superpowered ones, yes. And platforms like Causally, which leverage a massive knowledge graph, are reportedly helping pharmaceutical companies accelerate literature review and hypothesis generation by up to 90%. That's a massive speed up.
90%, wow.
Yeah. Then there's optimizing business processes and supply chains. MAS are being used here to manage inventory dynamically, forecast demand more accurately by integrating diverse data sources, and optimize logistics in real time. Some sources point to real-world case studies. A major retailer reportedly reducing stockouts by 30% using an agent-based system, a logistics company cutting fuel costs by over $500,000 annually through better routing managed by agents.
Real bottom line impact.
Absolutely. In finance, beyond the trading examples, firms are reporting things like a 40% reduction in trade execution time using multi-agent systems for algorithmic trading and order routing. And even in customer service, multi-agent systems are being deployed. They can handle initial interactions, gather information, potentially resolve simpler issues autonomously, or intelligently route complex cases to the right human expert. Some claims suggest autonomous resolution of up to 90% of conversations, saving human support teams huge amounts of time, maybe 70–80%.
That's a huge range of applications: software, science, logistics, finance, customer service. Yeah. Despite all this diversity, is there a common thread running through these applications? What's the core capability that makes MA suitable for such different problems?
That's a great question. If we connect this all to the bigger picture, the unifying theme seems to be handling complex coordination under uncertainty.
Right.
Whether you're coordinating software developers, molecules in a simulation, trucks on a road network, or financial trades, the fundamental challenge is often managing interactions between multiple entities with limited information in a dynamic environment.
So the coordination patterns are transferable.
It seems so. The architectural patterns, the communication strategies, the ways of managing shared knowledge, the solutions developed for coordinating, say, software agents, are proving surprisingly transferable to coordinating physical assets or scientific discovery processes. This cross-domain pollination of ideas is a really powerful accelerator for the whole field.
Interesting. And looking ahead, what's the trajectory?
Looking to the future, many analysts predict the rise of the agentic enterprise. Gartner, for instance, has some bold predictions. They estimate that by 2028, about a third, 33% of enterprise software applications will include agentic AI capabilities. And perhaps even more strikingly, they predict that 15% of daily work decisions could be made autonomously by AI agents by that time.
15% of daily decisions made by AI.
That's the prediction. It suggests a fundamental redefinition of human roles in the workplace. Humans likely shift towards higher-level strategic functions, setting goals, overseeing the AI teams, handling complex exceptions, managing the ethical considerations, working more in partnership with these AI agent teams rather than doing all the execution themselves.
Wow. Okay. From stateless text generators just a few years ago to these collaborative digital workforces making business decisions, discovering drugs, writing software, we've really taken a deep dive today into the architecture, the collaboration patterns, the frameworks, and the incredible, sometimes unpredictable intelligence that seems to be emerging from these LLM-powered multi-agent systems. It paints a picture of a future where AI isn't just a tool you use, but potentially a teammate, a specialist collaborator, maybe even a debater helping you make better decisions. So let me leave you, our listener, with this thought. What does this all mean for you? Given the power of these systems to not just perform tasks, but to actually engineer social dynamics within their own interactions, and given the constant potential for emergence of new, unpredictable behaviors, what do you think are the most critical ethical guardrails we absolutely need to put in place right now as these agentic enterprises start to become our reality?
That really is the crucial consideration moving forward. As we build towards these increasingly autonomous, potentially self-governing digital economies or collaborative systems, how do we ensure that the very culture we are implicitly or explicitly engineering into these multi-agent systems through their prompts, their reward functions, their architectures, is one that consistently and reliably prioritizes beneficial and ethical outcomes for humanity? The responsibility, I think, lies not just in the technical feat of building them, but in the foresight and wisdom required to consciously shape the emergent societies they will inevitably form. That's the ongoing challenge.